There is a star at the center of our solar system that we have studied longer than we have been human. We have pointed instruments at it, launched satellites toward it, built entire civilizations around its rhythm. We have mapped its surface down to individual plasma loops smaller than the state of Texas. We have sent probes through its outer atmosphere and returned data so detailed that scientists have spent entire careers parsing a single dataset from a single solar event on a single Tuesday afternoon in 1989. And yet, there are things the sun has not told us. Not because we haven't asked. We have, relentlessly, for decades. With the most sophisticated space-based observatories ever constructed by human hands, we have watched it wake up every 11 years in its regular cycle of fury and quiet, watched it breathe magnetic fields across 100 million miles of empty space, watched it fling billion-ton clouds of plasma outward at 1,000,000 miles per hour. We have watched all of this, and we still cannot fully explain what we are seeing. The sun is hiding something. Several somethings, actually, and the deeper we look, the larger those hidden things become. Not just scientifically interesting, not just academically puzzling, large in the way that matters for life on this planet, large in the way that comes with a timeline. That's what this is about, not the sun in the abstract, not the general wonder of stellar physics. This is about specific things the sun is withholding from our models, from our predictions, from our understanding, and about what each of those things means for a clock that is already ticking. Some of those clocks run for billions of years, some run for decades. One of them might already be running out. Let's start at the beginning. Not the sun's beginning. That was 4.6 billion years ago, and there was no one to watch. Let's start at the beginning of our confusion, the moment we realized that the thing we thought we understood was far more complicated than we had assumed. That moment has a name. It's called the solar neutrino problem. And it began in the 1960s, and it did not resolve cleanly until the early 2000s. And the resolution, when it finally came, opened a door we are still walking through today. Here is the problem, as it was first understood. The sun generates energy through nuclear fusion at its core. Hydrogen nuclei are crushed together under incomprehensible pressure and temperature, roughly 15 million degrees Celsius at the center, and fused into helium. This process releases energy in the form of photons and, crucially, particles called neutrinos. The neutrinos are important because they escape the sun almost instantly. A photon created in the solar core can take 100,000 years to random walk its way to the surface through the dense plasma. A neutrino passes through the entire sun in about 2 seconds. They arrive at Earth in a little over 8 minutes from the moment of their creation. This meant that if you could detect solar neutrinos, you could look directly into the heart of the sun in something close to real time. Not at the surface, not at the atmosphere, at the core where the fusion was actually happening. In 1967, physicist Raymond Davis Jr. built a detector in a gold mine in South Dakota, a tank filled with 100,000 gallons of dry cleaning fluid. He was looking for the signature of solar neutrinos striking chlorine atoms and converting them to argon. He ran the experiment. He waited. He counted the argon atoms. There weren't enough. The sun should have been producing a certain number of neutrinos based on every model of its nuclear furnace that had ever been constructed. Davis was detecting roughly a third of that number. Not close. Not within the margin of error. About a third. For 30 years, this was called the solar neutrino problem. Some physicists suggested Davis's detector was wrong. Some suggested the models of the sun's core were wrong. Some suggested, and this was the option that turned out to be correct, that something strange was happening to the neutrinos themselves during the 8-minute journey from the sun to the Earth. What was actually happening is that neutrinos oscillate. They come in 3 types: electron neutrinos, muon neutrinos, and tau neutrinos, and they change between those types as they travel. Davis's detector could only catch electron neutrinos. The sun was producing them at the rate the models predicted. By the time they arrived at Earth, a large fraction had become muon or tau neutrinos, invisible to his instrument. In 2001, the Sudbury Neutrino Observatory in Canada detected all 3 types simultaneously and proved the oscillation hypothesis. The solar models were right. The detector had just been seeing part of the picture. Here is why this matters more than it might appear. The resolution of the solar neutrino problem felt like closure. It felt like the mystery was solved. The sun's core was working exactly as predicted. The missing neutrinos had simply transformed in transit. Case closed. But the resolution required that neutrinos have mass. In the standard model of particle physics, the foundational framework describing every particle and force we know about, neutrinos were predicted to be massless. The oscillation discovery proved they weren't. This is a crack in the most successful theoretical framework in the history of physics. It is a small crack, but cracks in foundational frameworks have a way of being larger than they appear from the outside. And the sun, it turned out, was just getting started. The next mystery is older than the neutrino problem, but was not understood as a mystery until relatively recently. It is called the coronal heating problem, and it is, in many ways, more fundamentally disturbing. You know that temperature generally decreases as you move away from a heat source. Hold your hand near a flame and pull it back. It gets cooler. This is thermodynamics. It is not a subtle rule. It is one of the most basic behaviors of energy transfer in the universe. The sun violates this. The surface of the sun, the photosphere, the layer we see as the bright disk, is approximately 5,500 degrees Celsius. Move outward from the surface into the lower atmosphere. The temperature drops, as you would expect. Continue outward into the outer atmosphere, the corona, the ghostly white halo visible during a solar eclipse. The temperature rises again, dramatically, impossibly. The corona reaches temperatures between 1 and 3 million degrees Celsius. Some localized regions hit 10 million. The sun's outer atmosphere is 200 times hotter than its surface. This makes no physical sense by any ordinary thermodynamic logic. If you are standing in front of a campfire and you back up, you do not suddenly find yourself in a furnace. Yet this is exactly what the sun is doing. The energy is flowing outward from the surface into the corona, which means it is flowing from a cooler region into a hotter one. That is the wrong direction. We have known about this since the 1940s. We have been trying to explain it ever since, more than 80 years. We have sent spacecraft specifically designed to study it, most recently the Parker Solar Probe, which NASA launched in 2018 and has been conducting the most daring close approaches to the Sun in history, swooping to within a few million miles of the solar surface. Parker has already overturned multiple assumptions about the solar wind and coronal structure. It has given us data that nobody fully expected. And the coronal heating problem remains unsolved. There are competing hypotheses: wave-based heating, where magneto-hydrodynamic waves carry energy from the surface into the corona; nanoflare heating, where countless tiny magnetic reconnection events release small bursts of energy that cumulatively heat the corona to its observed temperature. Both are scientifically plausible. Both are supported by some observational evidence. Neither has been conclusively established as the dominant mechanism. Parker's most recent data suggests both processes may be occurring simultaneously in different regions, which is deeply unsatisfying if you want a clean answer, and deeply interesting if you want to understand what the sun is actually doing. Why does this matter beyond scientific curiosity? Because the corona is the source of everything that comes out of the sun and affects us. The solar wind, the constant stream of charged particles flowing outward through the solar system, originates in the corona. Coronal mass ejections, those billion-ton plasma eruptions that can knock out power grids on Earth, come from the corona. The sun's magnetic field, which extends throughout the entire solar system and shapes the heliosphere that protects us from cosmic radiation, is structured by coronal processes. We cannot fully predict solar behavior because we cannot fully explain what the corona is doing or why it does it. And solar behavior, specifically the most violent events the sun is capable of, has a timeline that concerns people who build the infrastructure that modern civilization depends on. That timeline comes next. But first we need to understand one more hidden thing, because it is perhaps the most fundamental of all. We do not actually know what is happening in the sun's interior in real time. Think about that for a moment. The sun has been the center of human astronomical attention for as long as humans have existed. We have been doing modern solar science for more than a century. We have instruments in space that cost hundreds of millions of dollars specifically designed to observe the sun in every wavelength, from radio waves to gamma rays. And we cannot see inside it. The photons we receive from the sun, the light and radiation that all of our telescopes detect, come from the very outermost layer. Below the photosphere, the plasma is opaque. The sunlight you see on a given day was generated by fusion events that happened approximately 100,000 years ago, slowly diffusing outward through the convective zone and radiative zone before finally escaping from the surface. The neutrino window we discussed earlier gives us a near real-time probe of the core, but neutrinos carry limited information. They tell us the fusion rate in the core. They do not tell us about the dynamics of the plasma, the behavior of the convective zone, the detailed structure of the magnetic fields threading through the interior, or the subsurface activity that precedes surface events like solar flares and coronal mass ejections. There is a technique called helioseismology that analyzes the way sound waves propagate through the sun's interior, using subtle oscillations in the surface to infer what lies beneath. Similar to how seismologists use earthquakes to study Earth's interior. This technique has been remarkably productive. It has given us three-dimensional maps of the solar interior, helped reveal differential rotation rates at different depths, and confirmed the basic layered structure of the sun. But helioseismology is limited in spatial resolution and in the timescales it can probe. It is a blurry image of an enormously complex system, and recent years have revealed that the blurry image contains features we did not expect. In 2021, a team of researchers published results suggesting the existence of large-scale flows in the deep solar interior, massive convective currents called giant cells that had been predicted by solar models for decades. The models said these giant cells should be large, coherent, and detectable by helioseismology. When scientists specifically looked for them, they found that the giant cells appeared to be dramatically weaker than expected. Either the models are wrong about convection in the solar interior, or there is something else going on that the models are not capturing. This is important for a specific reason. The Sun's magnetic field, which drives almost everything we care about when it comes to solar activity, from the 11-year cycle to the most violent eruptions, is generated by the interaction between the Sun's rotation and its internal convective flows. This process is called the solar dynamo. If we do not understand the convective flows, we do not fully understand the dynamo. If we do not fully understand the dynamo, we cannot reliably predict solar activity. And solar activity is not a purely academic matter. There is a specific class of solar events that represents a genuine civilizational risk, and the probability of one occurring on a timescale relevant to human infrastructure planning is not zero. It is not even reassuringly small. These events are called superstorms, and they have happened before. The most well-documented historical case occurred in September 1859, and it has a name: the Carrington event. On September 1st and 2nd of 1859, British astronomer Richard Carrington observed an intensely bright flare erupting from a large sunspot cluster. Within hours, the effects began arriving at Earth. The aurora borealis was visible as far south as Cuba and Hawaii. Telegraph systems across North America and Europe failed. In some cases, they failed dramatically. Operators received electrical shocks, telegraph paper caught fire. Some telegraph systems continued sending messages even after operators disconnected the batteries, powered entirely by the induced currents from the geomagnetic storm. In 1859, the telegraph was the most advanced piece of electrical infrastructure on Earth. Nothing else was vulnerable. In 2025, the electrical grid, satellite networks, internet infrastructure, GPS systems, aviation communications, financial transaction networks, and emergency response systems are all vulnerable. A Carrington-scale event striking today would be categorically different from one that struck in 1859. The National Academy of Sciences estimated in 2008 that a Carrington-equivalent event could cause between $1 and $2 trillion in damage in the United States alone, with recovery times measured in years, not weeks. The grid is not hardened against this. Most satellites have minimal shielding against extreme particle flux. GPS would likely be disrupted for extended periods. Here is the timeline question that matters. How often do Carrington-scale events occur? The answer is deeply uncomfortable. Based on historical records, ice cores, tree ring records, and the known history of the Sun's activity, researchers have estimated that events of Carrington magnitude or larger occur roughly once every 100 to 200 years. Some analyses of extreme events visible in ice core data suggest that events far larger than Carrington have occurred, events potentially 10 times more powerful, with a recurrence timescale of perhaps 1,000 years. It has been 166 years since the Carrington event. We are within the recurrence window. In July 2012, a Carrington-scale coronal mass ejection erupted from the Sun. It passed through the region of space where Earth had been 9 days earlier. 9 days! If the ejection timing had been slightly different, if Earth had been at a slightly different point in its orbit, we would have experienced a direct hit. Daniel Baker of the University of Colorado, who led the study of that 2012 event, was direct in his assessment. He described the miss as a cosmic bullet dodging and noted that the probability of a Carrington scale hit on Earth in any given decade is not trivial. Some estimates place it at roughly 12% per decade. 12% per decade. The Sun is not hiding the fact that it is capable of this. The data is there, the historical record is there. What the Sun is hiding is the specific timing. And that is the cruelest kind of hiding, because it means we must live indefinitely under that probability without being able to prepare for a specific date. Unless, of course, we can crack the prediction problem. Unless the things hidden deeper in the Sun, in its interior convection, in its coronal dynamics, in the physics of its magnetic field generation, can be understood well enough to give us warning. Not years of warning, not decades. Even days of warning would allow satellites to be repositioned, grid operators to reduce load, critical systems to be protected. That warning requires understanding what the Sun is hiding at a deeper level than we have reached so far. We are trying. The Parker Solar Probe has already changed our picture of the near-Sun environment in ways nobody predicted. The European Space Agency's Solar Orbiter, launched in 2020, is on a trajectory that will eventually allow it to image the Sun's polar regions directly for the first time, regions that play a critical role in the magnetic field reversal that occurs every 11 years. The Daniel K. Inouye Solar Telescope in Hawaii, which achieved first light in 2020, has produced the highest resolution images of the solar surface ever made. Images that show structures smaller than 30 kilometers in a star that is 1.4 million kilometers across. Every one of these instruments is finding things that don't fit neatly into our existing models. Not in ways that overturn everything we know, in ways that reveal how much of the picture we were missing. There is a pattern here, and it matters to understand it before we go further. The Sun's mysteries are not isolated puzzles. They are connected. The neutrino problem pointed to gaps in particle physics. The coronal heating problem points to gaps in magneto-hydrodynamics and energy transfer. The interior convection puzzle points to gaps in our dynamo models. The dynamo gaps cascade into prediction failures for solar activity. The prediction failures leave us exposed to events that have a recurrence timeline we are already inside. The hidden things are not separate, they form a structure. And that structure has a shape that we are only now beginning to see clearly. Part of that shape involves a discovery that was made less than a decade ago and has not yet received the public attention it deserves. It involves the Sun's magnetic field at a scale far larger than the 11-year cycle. It involves a rhythm that operates over centuries, and evidence that we may be approaching a specific phase of that rhythm that changes the risk calculus significantly. It involves something called the extended solar cycle, and a hypothesis about the Sun's behavior over the next several decades that some researchers believe is the most important thing in solar physics right now. Before we get to that, though, we need to spend time with something that the Sun is hiding in plain sight. Something that has been measured and documented and largely ignored by everyone except the specialists who study it. Something that represents in a very direct and unambiguous way the Sun's agenda, not for the next decade or the next century, but for the next 5 billion years. The Sun is changing, not dramatically, not in a way you would notice in a human lifetime or 1,000 human lifetimes, but measurably, quantifiably, in a direction that has consequences. It is getting brighter. Every billion years, the Sun's luminosity increases by approximately 10%. Over the course of its main sequence lifetime, The long central period when it burns hydrogen in its core, it will approximately double in total energy output. It started dimmer than it is now, and it will end far brighter. This creates a puzzle about the past, the faint young sun paradox, which we will explore in detail, and a certainty about the future. The sun's increasing brightness is not a catastrophic event with a single date. It is a gradient. But that gradient has thresholds, and those thresholds have timelines, and at least one of those timelines falls within the range of a question a human being might reasonably ask: how long does this planet stay habitable? That question has an answer. It is not infinite, it is specific, and it is closer than most people imagine. We will get to that number. But first we need to understand how we know what we know about the sun's past, because the past is where the deepest hidden thing of all resides, the thing the sun's own history reveals about what happens to worlds like ours when a star like ours changes the way the sun is already changing. The past holds a warning. The sun encoded it. We are only now learning to read it. 4 billion years ago, the sun was approximately 70% as luminous as it is today. Hold that number for a moment. 70%. By any reasonable calculation, Earth at that luminosity should have been frozen solid. The energy arriving from a younger, dimmer sun would have been insufficient to keep liquid water on the surface. The oceans should not have existed. The early atmosphere, whatever it looked like, should have been a frozen shell over a world of ice. And yet, the geological record is unambiguous. There was liquid water on Earth 3.8 billion years ago. There were oceans. There was chemistry complex enough to produce the precursors of life. The rock record from that era contains formations that can only be explained by the presence of flowing, liquid water at the surface. There are ancient stromatolites, layered structures built by microbial mats, dating to roughly 3.5 billion years ago, requiring not just liquid water, but a relatively stable, temperate environment. The sun was too dim for this to be possible, and yet it was possible because it happened. This is the faint young sun paradox, first clearly articulated by Carl Sagan and George Mullen in 1972, and it remains one of the most actively debated problems in planetary science. It sits at the intersection of solar physics, atmospheric chemistry, geology, and biology. It is not a small puzzle. It is a question about how the Earth was able to be Earth when the sun was not yet the sun it is now. The most obvious solution is that the early Earth had a much thicker greenhouse atmosphere. More carbon dioxide, more methane, more water vapor. Greenhouse gases that trapped enough additional heat to compensate for the dimmer sun. This is almost certainly part of the answer. Early Earth's atmosphere was very different from today's, dominated by carbon dioxide and nitrogen without significant oxygen until the Great Oxidation Event approximately 2.4 billion years ago. The greenhouse effect would have been substantially stronger. But when scientists try to calculate how much greenhouse warming would be required to fully compensate for a sun 30% dimmer, the numbers are uncomfortable. You need a lot more greenhouse gas than early Earth's atmosphere appears to have contained, based on the geological proxies available. The carbon and oxygen isotope records, the mineral assemblages in ancient sediments, the nitrogen isotope signatures, they all paint a picture of an early atmosphere that was greenhouse enhanced, yes, but perhaps not enhanced enough to do the entire job. There are other proposed solutions. Early Earth may have had lower cloud cover, which would reduce the amount of sunlight reflected back into space. The early ocean may have been more extensive, with less continental landmass to reflect sunlight. The Moon was closer, potentially affecting tidal dynamics and atmospheric mixing in ways that are difficult to model. The Earth's rotation was faster, which changes atmospheric circulation patterns. None of these individually, and perhaps not all of them together, seem to fully close the gap. And this matters because it means we may be missing something about the Sun's behavior on geological timescales. Something the Sun was doing differently in its youth that compensated for its lower luminosity. Something the models are not capturing. One hypothesis that has received serious attention in recent years is that the young Sun was more massive. Stars lose mass through their stellar winds, the constant outflow of charged particles from the corona that we experience as the solar wind today. If the young Sun had a significantly stronger stellar wind, it would have been losing mass faster, which means it was slightly more massive in the past, which means its gravitational compression was slightly greater, which means its core was slightly hotter, and its fusion rate slightly higher, which means it was slightly more luminous than the simple age-luminosity relationship suggests. This is not a fringe idea. It has been explored in published papers and modelled in detail. The problem is that it requires the young Sun's mass loss rate to have been substantially higher than anything we can directly measure or confirm from solar analogues, stars similar to the Sun, but at different ages. The mass loss rate that would be needed to solve the faint young Sun paradox appears to be at the outer edge of plausibility, and accepting it creates other problems. A more massive young Sun would have created different orbital dynamics for the early planets, potentially affecting the architecture of the solar system in ways that don't match what we observe. The paradox remains open. Why does an unresolved 4-billion-year-old puzzle matter for the future? Because the same mechanisms that governed the young Sun's interaction with early Earth are governing the modern Sun's interaction with Earth right now, and will govern the future Sun's interaction with a warming Earth for as long as the planet remains habitable. If we are missing something fundamental about the Sun-Earth climate system in the past, we may be missing something fundamental about it in the present and future as well. The Sun is the dominant driver of energy input into Earth's climate system. This is not controversial. The total solar irradiance, the amount of energy the Sun delivers to the top of Earth's atmosphere, varies across the 11-year solar cycle by about 0.1%. That variation sounds tiny. It is tiny compared to the total energy budget. But the climate system is sensitive, and the ways in which solar variability interacts with atmospheric chemistry, cloud formation, and ocean circulation are not fully captured in current climate models. There is a specific solar-climate interaction that has been studied extensively and remains genuinely contested among researchers. It involves cosmic rays. The hypothesis, first advanced seriously by Danish physicist Henrik Svensmark in the 1990s, goes like this. The Sun's magnetic field, extended through the heliosphere, deflects a portion of the cosmic ray flux entering the solar system. When the Sun is more magnetically active, during solar maximum, more cosmic rays are deflected, fewer reach Earth. When the Sun is less active, solar minimum, the heliospheric shield weakens, more cosmic rays reach Earth. Cosmic rays, when they enter Earth's atmosphere, ionize atmospheric molecules. Ionized molecules can act as condensation nuclei for cloud formation. More ionization means potentially more low-level cloud cover. More cloud cover means more sunlight reflected back into space, which means cooler temperatures. If this chain is correct, then changes in solar magnetic activity over decades and centuries have a climate effect that operates through the cosmic ray cloud pathway, independent of the direct effect of total solar irradiance changes. CERN ran an experiment called CLOUD, specifically to test the microphysics of this hypothesis, whether cosmic ray ionization actually enhances the formation of aerosol particles that seed clouds under realistic atmospheric conditions. The results have been mixed and nuanced. Cosmic rays do appear to enhance nucleation of certain aerosol types under certain conditions. Whether the effect is large enough to significantly modulate global cloud cover and therefore global temperature remains under active investigation. What is not contested is that solar magnetic activity has varied significantly over the past several centuries, and those variations correlate with climate changes in ways that are difficult to fully explain through direct irradiance changes alone. The Maunder minimum, a period of extremely reduced sunspot activity between approximately 1645 and 1715, coincided with the coldest phase of what is called the Little Ice Age. The Thames froze solid, alpine glaciers advanced, growing seasons shortened across northern Europe. The correlation does not prove that solar activity caused the cooling. There were also significant volcanic eruptions during this period, and volcanic aerosols have a well-established cooling effect. Distinguishing the solar signal from the volcanic signal and from natural climate variability is genuinely difficult. But the correlation is there, and it is substantial enough that dismissing it entirely seems premature. Here is the connection to the present and the future. There is a body of evidence suggesting that the Sun may be entering a period of reduced magnetic activity over the coming decades. Not a Maunder minimum, necessarily, but a grand solar minimum, a period when the 11-year cycle is subdued, sunspot counts are lower, and the heliospheric magnetic field is weaker. The evidence for this comes from several directions. The solar cycle, 24, which ran from 2008 to 2019, was notably weak, the weakest cycle in a century. Solar cycle 25, which began in 2019, was predicted by some models to be similarly weak, though it has actually shown more activity than expected, which is itself an interesting departure from some forecasts. Longer period models that attempt to predict the behavior of the solar dynamo over multiple decades suggest that the Sun may be approaching a phase of reduced activity similar to the Dalton minimum of the early 1800s, or potentially deeper. Why does this matter against the backdrop of the other things we are discussing? Because a grand solar minimum would produce cooling pressure on the climate at a time when human greenhouse gas emissions are producing warming pressure. These two influences do not simply cancel each other. The climate system is not a linear balance sheet where you add one and subtract the other. But the interaction between natural solar variability and anthropogenic forcing is a genuine area of scientific research, and the possibility of a solar minimum in the coming decades adds a layer of uncertainty to climate projections that is rarely discussed publicly. More importantly for the long-term picture, if the Sun enters a prolonged quiet phase, the cosmic ray flux reaching Earth increases. A weakened heliospheric magnetic field means more galactic cosmic rays penetrating into the inner solar system. More cosmic rays reaching Earth means more ionization of the upper atmosphere. The effects on atmospheric chemistry, on cloud formation, on the ozone layer, these are real and measurable, even if their magnitude is debated, and there is a deeper layer still. The heliosphere, that vast bubble of solar wind and magnetic field that surrounds the entire solar system, acts as a shield against not just galactic cosmic rays, but against interstellar material. We are moving through the galaxy constantly, and the interstellar medium is not uniform. There are regions of higher density, higher radiation, higher particle flux. The heliosphere deflects most of this. A weakened heliosphere during a period of reduced solar activity is a less effective shield. We passed through a slightly denser region of the interstellar medium relatively recently in astronomical terms, and there is evidence in the geological record, in ocean sediment cores, in cosmic ray-produced isotopes like beryllium-10 and chlorine-36, of periods when the heliospheric shield was weaker and the cosmic ray flux at Earth was higher. These periods correlate, loosely, with periods of biological stress in the fossil record, not mass extinctions, but elevated mutation rates, elevated cancer rates in organisms, subtle shifts in evolutionary pressure. The Sun is connected to the galaxy in ways that are rarely part of the public conversation about solar science. The heliosphere is not a permanent fixture. It breathes with the solar cycle. It fluctuates with solar magnetic activity. And over the Sun's 230 million-year orbit around the galactic center, we pass through environments that test it in ways that a short, human, observational window cannot capture. All of this, the faint young sun paradox, the solar climate connection, the heliospheric shield, is backdrop for a more immediate, hidden story. The story of what the Sun is going to do specifically over the next century, over the lifetime of infrastructure being built today, over the generations of people who will inherit the world we are currently managing. To tell that story properly, we need to talk about the solar cycle in more depth than it usually receives. Not just the 11-year cycle everyone has heard of. The longer cycles. The ones that operate on timescales of decades and centuries and that appear to govern how dangerous the peaks of those shorter cycles become. The 11-year sunspot cycle is a surface expression of something happening deep inside the Sun. Magnetic field lines generated in the interior by the dynamo process rise through the convective zone and emerge at the surface, constraining and shaping the plasma above them. Sunspots are concentrations of intense magnetic field, so intense that they suppress the convective heat transport in their immediate area, making that region cooler and therefore darker than the surrounding photosphere. They appear dark against the solar disk, but would be brilliant objects on their own. Each sunspot is still thousands of degrees, still emitting enormous energy. They just look dark by comparison. During solar maximum, sunspot counts are high. The surface is threaded with intense magnetic structures. Flares are more common. Coronal mass ejections are more frequent and more powerful. The solar wind is stronger and more variable. During solar minimum, the surface quiets. Sunspots are sparse or absent. The magnetic field takes on a simpler, more ordered structure. The solar wind is calmer and more uniform. This cycle repeats. Roughly every 11 years, the Sun's magnetic field reverses, the north and south magnetic poles swap, and a new cycle begins. This is familiar. This is Solar Physics 101. What is less familiar is the evidence that these 11-year cycles are themselves organized into longer patterns. The Gleisberg cycle, named after German astronomer Wolfgang Gleisberg, is a modulation of the 11-year cycle with a period of approximately 80 to 90 years. During a Gleisberg maximum, the peaks of the 11-year cycles are higher than average. During a Gleisberg minimum, the peaks are lower. Above the Gleisberg cycle, there appears to be a longer modulation with a period of approximately 200 to 230 years, sometimes called the De Vries or Suez cycle. Above that, a cycle of approximately 2,000 years. Above that, Evidence from cosmogenic isotope records suggests modulation on timescales of several thousand years. These longer cycles are real in the sense that they appear in the isotopic record. Their physical mechanism, how they arise from the solar dynamo, what processes in the solar interior generate them, is poorly understood. The dynamo models that successfully reproduce the 11-year cycle have difficulty naturally generating the longer periodicities. This is another place where the sun's interior is hiding something from us. What these longer cycles mean practically is this. The danger level of a given solar maximum depends on where that maximum falls within the larger, nested cycles. A solar maximum that occurs at the peak of a Gleisberg cycle during a de Vries cycle maximum is a fundamentally different animal from a solar maximum that occurs during a grand minimum phase. The difference between a typical active cycle and an extreme one is not just a factor of 2 in sunspot numbers. It can be an order of magnitude difference in the frequency and intensity of major geomagnetic events. We know from the isotopic record that the second half of the 20th century represented an unusually high level of solar activity, often called the modern grand maximum. Solar cycles 18 through 23, spanning roughly 1944 to 2008, were collectively among the strongest in several centuries. The infrastructure that was built and the vulnerability assessments that were made were based on conditions during a period of exceptional solar activity, which sounds paradoxical. You would expect high activity to produce more incidents, more awareness of vulnerability. But the modern grand maximum also coincided with the construction of the most extensive and sophisticated electrical infrastructure in human history, infrastructure that was never designed with the most extreme solar events in mind, because the engineers were working in a period that, while active, did not produce a direct hit of Carrington magnitude. Now, the modern grand maximum appears to be ending. The question of what comes next, whether the coming decades bring continued moderate activity, a return to historical average levels, or a deeper minimum, is the question that drives solar prediction research, and it is a question the Sun has not yet answered clearly. The Parker Solar Probe and Solar Orbiter are not just academic exercises. They are reconnaissance missions into the physics of the thing that most directly threatens modern civilization's continuous operation. The data they are returning is being analyzed by researchers who understand that the difference between a predicted and an unpredicted Carrington scale event is the difference between managed disruption and civilizational catastrophe. There is one more layer to add before we reach the deepest hidden thing of all, and it involves a region of the Sun that has barely been observed in the entire history of solar science. A region that the models say should be doing something specific and important, a region that Solar Orbiter is about to image directly for the first time, the poles. The Sun's polar regions are where the magnetic field that drives the entire 11-year cycle is born and dies. At the end of each cycle, as the old magnetic field decays, the remnants of active region magnetic flux, the leftover field from decayed sunspot groups, migrate poleward and accumulate at the poles. The strength of this polar field at solar minimum is one of the best predictors we have for the strength of the upcoming solar cycle. A stronger polar field at minimum predicts a stronger maximum. A weaker polar field predicts a weaker cycle. This is not just a statistical correlation. There is a physical mechanism. The polar fields seed the new toroidal field that will emerge as sunspots in the next cycle. The poles are the seed bank for the next 11 years of solar activity. and we have never directly imaged them from above. Every spacecraft that has observed the Sun has done so from near the ecliptic plane, the plane of Earth's orbit. The Sun's poles are tilted about 7 degrees relative to the ecliptic, and from Earth's vantage point we see them at a steep angle that severely limits what can be observed. It is like trying to read a page of text held almost parallel to your line of sight. You can make out the presence of something, but the details are lost. Solar Orbiter is in the process of raising its inclination relative to the ecliptic over a series of gravity assist maneuvers at Venus. By the late 2020s, it will reach an inclination of approximately 33 degrees. Not a direct overhead view, but dramatically better than anything achieved before. For the first time, we will see the Sun's poles with enough clarity to test the models that claim to understand what happens there. The models may not survive the encounter intact. There is a specific prediction that solar physicists have been making for decades about the Sun's polar regions, and it is a prediction that has never been directly tested because we have never had the instruments or the vantage point to test it. The prediction involves something called the polar crown filament channels. These are enormous structures, ribbons of cool, dense plasma suspended in the corona above the polar regions by magnetic field configurations that are, frankly, not fully understood. They form at high latitudes during each solar cycle, and they are believed to play a role in the polar field reversal that marks the transition between cycles. The models say they should behave in a specific way, forming, accumulating, and eventually erupting in a predictable sequence tied to the cycle phase. But the models were built on data from the ecliptic plane. They extrapolated to the poles from observations that could only see the polar regions obliquely. The assumptions baked into those extrapolations have never been independently verified. Solar Orbiter will verify them, or it will not, and the scientific community is quietly braced for the possibility that it will not, that the poles, when seen clearly for the first time, will show something the models did not predict. This is not pessimism, it is pattern recognition. Every time we have looked at a previously unobserved region of the Sun with significantly improved instrumentation, we have found surprises. The Parker Solar Probe found that the solar wind near the Sun is far more structured and turbulent than expected, with sudden reversals in the magnetic field direction called switchbacks that nobody predicted, and that are still not fully explained. The Inouye Solar Telescope revealed convective structures at the solar surface called convective cells at a resolution fine enough to show that the energy transport mechanisms are more complex than the standard models assume. SOHO and SDO revealed the complexity of active region magnetic topology in ways that made flare prediction harder, not easier, because the systems turned out to be more intricate than the models suggested. The Sun has a consistent record of being more complicated than we thought at every scale we examine it. What Solar Orbiter's polar observations will add to this picture is, potentially, a fundamental revision of how we understand the solar dynamo's most sensitive component. The polar fields are the reset mechanism. They are where one cycle ends and the next begins. If they behave differently than the models predict, if the filament channels erupt at different times or in different configurations, or if the polar magnetic flux distribution is structured in ways the models don't capture, then the predictive framework we use for solar cycle forecasting needs to be rebuilt from that foundation. And solar cycle forecasting is not just an academic exercise, it is the basis for planning satellite launches, for scheduling maintenance windows on power grid infrastructure, for positioning insurance risk models that cover damage from geomagnetic events, for designing the radiation shielding on crewed spacecraft. The International Space Station's orbital altitude is partially managed around the solar cycle because during solar maximum, increased solar EUV radiation causes Earth's upper atmosphere to expand slightly, increasing drag on the station and requiring more frequent reboosts. The solar cycle is built into operational planning at NASA, ESA, and every commercial launch provider. A broken predictive framework has operational consequences that cascade through every domain that depends on space-based infrastructure. And space-based infrastructure is not a peripheral concern. There are currently more than 9,000 satellites in Earth orbit. That number is projected to exceed 100,000 within the next decade, driven primarily by large constellation deployments from commercial operators. The Starlink constellation alone has plans for tens of thousands of satellites. Every one of those satellites operates in an environment shaped by solar activity. Every one of them is vulnerable, in varying degrees, to the kind of extreme space weather event that the Sun is capable of producing and that we cannot yet reliably predict. There is a specific scenario that space weather researchers worry about more than any other. Not the Carrington event itself, as destructive as that would be. A scenario where a moderate but not extreme geomagnetic storm disrupts satellite positioning data at a critical moment for aviation or financial clearing or autonomous systems. The catastrophic failure mode is not necessarily the spectacular one. It may be a cascading failure of interdependent systems that individually have some resilience but collectively do not. A storm that is not large enough to make headlines, but that exploits the gaps in our hardening at exactly the wrong moment. This is a well-understood concept in systems engineering. It is called a common mode failure. And it is the reason nuclear plants design against seismic events that might simultaneously disable backup systems that were assumed to be independent. The solar threat to modern infrastructure is a common mode threat of extraordinary breadth. It can simultaneously affect every satellite in a particular orbital band, every long-distance power transmission line at certain latitudes, every high-frequency radio communication link, every GPS receiver on the planet. We have not fully stress-tested our systems against this. The evidence for this is simple. When researchers attempt to model the cascading effects of a Carrington-scale event on modern infrastructure, they consistently find that the models are limited by incomplete knowledge of interdependencies. We do not have a comprehensive map of which systems fail if which other systems fail simultaneously. The grid operators, the satellite operators, the telecommunications companies, the financial networks, they each know their own vulnerabilities, but the cross-sector picture is incomplete. The Sun does not care about sector boundaries. Now, let us move to a layer of the hidden story that operates on a different timescale entirely. Not decades, not centuries, billions of years, because the Sun's most significant secret is not what it will do in the next solar maximum. Its most significant secret is written into its own lifespan, and it concerns not a disaster, but a transformation so slow it is almost impossible to think about as a threat, and yet so certain that every calculation about the long-term future of life on Earth must account for it. We established earlier that the Sun is getting brighter at a rate of roughly 10% per billion years. This has been true for the Sun's entire main sequence life, and it will continue to be true for the remaining 5 billion years or so before the Sun exhausts its core hydrogen supply and begins the transition that will eventually render it a red giant and then a white dwarf. 10% per billion years sounds gradual. It is gradual by human standards. But Earth's climate system is sensitive, and the habitable zone, the range of orbital distances from the Sun at which a planet can maintain liquid water on its surface is not fixed. It moves outward as the Sun brightens. Earth, at its current orbital distance, is already near the inner edge of the conservative habitable zone. As the Sun continues to brighten, that edge moves outward. Eventually, it moves past Earth's position. The question of when Earth loses its habitability due to solar brightening has a specific technical answer, and it is one of the more sobering numbers in planetary science. Based on current models of Earth's climate system and the carbon silicate cycle, the geological thermostat that regulates atmospheric CO2 on timescales of hundreds of millions of years, the Earth will likely become uninhabitable for complex, multicellular life within approximately 500 million to 800 million years. Not because the oceans boil, that happens later, but because the increasing solar luminosity will drive a feedback loop in the carbon cycle that eventually reduces atmospheric CO2 to levels too low to support plant photosynthesis. Here is how that feedback loop works. As the Sun brightens, Earth warms. Warmer temperatures increase the rate of chemical weathering of silicate rocks, a process where CO2 from the atmosphere reacts with rocks and gets sequestered. This is the planetary thermostat. More heat leads to more weathering, which removes CO2, which reduces the greenhouse effect, which cools the planet back down. The thermostat has kept Earth's climate within habitable bounds for billions of years despite the Sun's gradual brightening. But the thermostat has a flaw. It can only remove CO2. It cannot add it. The only significant natural source of atmospheric CO2 on geological timescales is volcanic outgassing, which is expected to gradually decline as Earth's interior cools and tectonic activity slows. As the Sun continues to brighten, the weathering thermostat is forced to draw CO2 down further and further to compensate. Eventually, CO2 falls below approximately 150 parts per million, the threshold below which C3 photosynthesis, used by the vast majority of plants, cannot function. When plant photosynthesis fails, the food chains collapse. Not immediately, not all at once, but the trajectory is clear and it is irreversible on any timescale relevant to biology. Most complex multicellular life on the surface depends, directly or indirectly, on photosynthesis. Remove photosynthesis and you remove the foundation. Some organisms are more resilient. C4 plants, which include corn, sugarcane, and various grasses, can function at lower CO2 levels. Microbes that derive energy from chemical reactions rather than sunlight, chemolithotrophs, are effectively immune to this particular threshold. Life as a planetary phenomenon likely persists long after complex surface life has ended. Microbial ecosystems in the deep ocean, in hydrothermal vent systems, in subsurface rock formations. These may continue for billions of years after the last tree has died. But the era of complex surface life, of animals, of ecosystems as we recognize them, of anything resembling the biosphere we inhabit, ends somewhere in the window of 500 million to 800 million years from now. This is not a distant abstraction. In geological terms, 500 million years is approximately the time since the Cambrian explosion, the event that produced the vast majority of animal body plans that have ever existed. The entire history of complex animal life on Earth fits inside that window. We are not discussing some remote cosmological future. We are discussing a timeline comparable to the entire span of animal evolution, and 500 million years is the pessimistic end of the estimate. Some models push the outer limit of complex life's habitability to closer to 1 billion years. The uncertainty in these estimates is large because the carbon cycle models involve numerous parameters: weathering rates, volcanic outgassing rates, the evolution of the biosphere itself, that are difficult to constrain precisely. What is not uncertain is the direction. The sun is brightening. The thermostat has a floor. The floor will be reached. There is a deeper implication here that connects the long-term future to the faint young sun paradox we discussed earlier. The same carbon silicate weathering cycle that will eventually push CO2 too low is the cycle that maintained habitable conditions on early Earth despite the sun being 30% dimmer. The thermostat worked in reverse in the early solar system. Less solar heat meant less weathering, meant CO2 accumulated to higher levels, means a stronger greenhouse effect to compensate for the dimmer sun. The thermostat naturally keeps Earth habitable across a wide range of solar luminosities, but not an infinite range. And we are approaching one of its limits, slowly, but on a trajectory that has no reversal unless something intervenes. Which brings us to a question that planetary scientists have begun to take seriously in the past decade, not as science fiction, but as an engineering problem with a specific timeline. The question of whether a technological civilization could, in principle, adjust Earth's orbit outward as the sun brightens, moving the planet to compensate for increasing solar luminosity, maintaining habitable surface conditions by keeping pace with the moving habitable zone. The numbers have been worked out. They are not encouraging in their requirements, but they are not physically impossible. Moving Earth's orbit outward by a meaningful amount, say 1%, every 100 million years to roughly track the expanding habitable zone, requires enormous energy applied over very long time scales. The proposed mechanisms involve gravitational assists from redirected asteroids or comets using the gravitational influence of passing large bodies to slowly transfer angular momentum to Earth's orbit. These are not technologies we have. They are technologies that would require sustained civilizational capability over timescales that dwarf all of recorded history. Whether a civilization is capable of this is an open question that involves not just engineering, but sociology, stability, and the nature of very long-term planning. These are not comfortable questions, but they are real ones, and the timeline imposes a soft deadline, not for beginning the process, which could theoretically start much later, but for the civilization that would need to execute it to remain coherent and capable across millions of years of continuous effort. This is what the sun's gradual brightening means in its most explicit form. It is not a threat on a human timescale. It is a threat on the timescale of everything complex that has ever lived or will live on this world. And understanding it requires understanding the sun at a depth we have not yet achieved. There is one more dimension of the sun's hidden nature that we have not yet addressed, and it is perhaps the strangest. It involves not what the sun is doing now or what it will do in the future, but what it reveals about the structure of the universe simply by existing the way it does, by being a star of this exact type, at this exact age, in this exact location, burning at this exact rate. Because the sun is, by cosmic standards, remarkably ordinary. G-type main sequence star. Middle-aged, medium mass, moderate luminosity. These are not distinctive features. There are hundreds of billions of stars in the Milky Way alone, and a significant fraction of them are G-type main sequence stars. The Sun is not special by stellar classification, but it is special in ways that took decades of exoplanet research to make clear. The Sun's specific combination of properties, its mass, its age, its composition, its activity level, its position in the galaxy, turns out to be less common than the raw statistics of stellar populations suggest. Not unique, not miraculous, but notable. The Sun is unusually quiet for its type. Solar-type stars of the Sun's age span a wide range of activity levels, and the Sun sits near the low end of that distribution. It is what astronomers call a weakly active star. Its cycle amplitude is modest, its flare frequency is low compared to many solar analogues, and its long-term variability is subdued. This is good for us. A more active Sun, one that produced the flare and CME rates typical of the more active end of the solar analog distribution, would be a significantly more hostile environment for life. Some researchers have argued that the Sun's relative quiescence is a meaningful factor in Earth's biological history, that complex life may require not just a star in the right zone, but a star with the right temperament. The Maunder minimum we discussed earlier, that 70th century period of dramatically reduced solar activity, has an interesting flip side. If the Sun were stuck permanently in a Maunder-like state with very low activity and very weak cycling, the reduced ultraviolet output would affect the chemistry of Earth's ozone layer, which would affect the shielding of the surface from UV radiation. The relationship between solar activity and Earth's atmospheric chemistry is not linear and not intuitive. A very quiet Sun is not simply a safer Sun. It has its own set of consequences. The Sun's current activity level, in its current phase of the long-period cycles, represents something like a middle path, active enough to maintain a robust heliospheric shield, quiet enough not to regularly sterilize the inner solar system with extreme events. This balance is not guaranteed to persist. It reflects the current phase of the nested cycles we discussed, cycles that will continue to evolve, that will eventually push the Sun through phases both quieter and more active than anything in the historical record. And here is the thing about the hidden nature of those longer cycles. The data we have on the multi-century and multi-millennium solar cycles comes from proxies. Cosmogenic isotopes in ice cores and tree rings, records of historical aurora sightings, records of sunspot observations going back several centuries in Chinese, Korean, and European astronomical archives. These proxies give us a picture of relative activity, periods of higher and lower solar output, but they do not give us the physical mechanism. We can see the rhythm in the data. We cannot yet fully explain what is generating that rhythm in the solar interior. The answer, when it comes, will likely come from helioseismology combined with the new interior flow data from instruments like Solar Orbiter, combined with the increasingly precise measurements of the Sun's polar fields across multiple cycles. It will require observing the Sun across at least 2 or 3 complete 80 to 90-year Gleisberg cycles, a project that is longer than modern solar science has existed. We are partway through building the dataset that will eventually allow us to understand the multi-decade structure of solar behavior. In the meantime, we operate with models that are known to be incomplete, making predictions that are known to have significant uncertainty bands, building infrastructure that is known to be vulnerable to events that are known to be possible, but not precisely predictable in timing or intensity. This is not a counsel of despair. It is a description of where we are, and where we are includes capabilities that are genuinely improving. The warning time for a major geomagnetic event has expanded from essentially nothing in 1859, when the Carrington event arrived with no warning whatsoever, to roughly 15 to 60 minutes today, based on real-time monitoring of the solar wind from instruments at the L1 Lagrange point, the gravitationally stable location between Earth and the Sun, where NASA's ACE and D-ESCOVA spacecraft have been stationed. 15 to 60 minutes is not a lot of time to protect a planetary civilization, but it is more than zero, and the engineering of systems that can respond automatically to incoming space weather data, that can switch power routing, safe satellites, alert flight crews and pipeline operators, is advancing. The question is whether it is advancing fast enough, and whether the political and economic will exists to fund the hardening work before an event forces it. The Sun is hiding its timing from us. We know the event is coming. We do not know when. The entire history of solar prediction research is an attempt to shrink the uncertainty band around that unknown. And within that uncertainty band lives something we have not yet talked about directly, something that sits at the intersection of all the hidden things we have discussed: the interior mysteries, the coronal dynamics, the cycle modulations, the historical record of extreme events, something that represents the Sun's deepest secret, not because it is obscure or technical, but because its implications are so large that they tend to be discussed only in specialized literature, and almost never in the terms that make them legible to anyone outside the field. It is the question of what the Sun is actually capable of at its absolute extreme, not the Carrington event. Beyond the Carrington event, the question of whether the Sun, our Sun, the quiet, middle-aged, unremarkable G-dwarf we have been discussing, is physically capable of producing an event so extreme that it would not just disrupt modern infrastructure, but would directly threaten complex life on the surface of the Earth. The answer to that question is in the data, and the data says something that most people have not heard. In 2012, a team of researchers led by Carolus Schreiber at the Lockheed Martin Solar and Astrophysics Laboratory published a paper that received significant attention within the solar physics community and almost none outside it. The paper examined the physical upper limits of what the Sun is capable of producing in terms of flare and coronal mass ejection energy. They were not asking what the Sun typically does, they were asking what it can do, what the physics of the solar magnetic field, constrained by everything we know about how energy is stored and released in solar active regions, places as a ceiling on the most extreme possible solar event. The number they arrived at was approximately 10 to 20 times the energy of the Carrington event. 10 to 20 times. The Carrington event induced currents in telegraph wires strong enough to shock operators and set paper on fire. It produced aurora visible at the equator. It compressed Earth's magnetosphere to roughly half its normal size. And according to Schreiber's analysis of the energy available in extreme solar active regions, we have not seen the Sun's upper limit. What we experienced in 1859 was not the worst-case scenario. It was a large event, not the largest possible event. For context, consider the energy scaling. The damage potential of a geomagnetic storm does not scale linearly with storm intensity. The relationship between incoming solar energy and ground-level effects involves the magnetosphere, the ionosphere, and the coupling between the geomagnetic field and long-conducting structures, power lines, pipelines, undersea cables. This coupling is highly nonlinear. An event twice as energetic as Carrington does not produce twice the ground-level effects. It produces effects that are potentially an order of magnitude more severe because the magnetospheric compression is deeper, the induced currents are larger, and the storm duration is longer. An event 10 times more energetic than Carrington would not just damage the power grid, it would likely destroy significant portions of it in ways that require manufacturing replacements. Large transformers, which are the most vulnerable components, take 18 months to 3 years to manufacture and are not stockpiled in meaningful quantities anywhere in the world. A sufficiently extreme event could knock out grid infrastructure that would take years to replace. In a world where replacement requires functioning industrial supply chains that themselves depend on electricity. This is not a fringe assessment. It reflects the consensus of space weather researchers who have studied the infrastructure vulnerability question. The National Academy of Sciences report, the Lloyd's of London assessment of space weather risk, the work of the Jason Advisory Group for the US Department of Defense. They all arrive at broadly similar conclusions about the potential severity of an extreme space weather event. The disagreements are about probability, not about potential consequences. Now, let us add the layer that makes this more than a theoretical concern. In 2019, researchers published analysis of a solar event recorded in ice cores and tree ring data from the year 774 CE. It was first identified in 2012 by Fusa Miyake at Nagoya University, who noticed a sharp spike in carbon, 14 levels in Japanese cedar tree rings, a spike indicating a sudden massive increase in cosmic ray or high-energy proton flux arriving at Earth. The spike was global. It appeared in tree ring records from across the northern and southern hemispheres simultaneously. It was dated to 774 or 775 CE, and it was approximately 20 times larger than any event in the cosmogenic record from the past 10,000 years that could be attributed to solar activity. This event, now called the Miyake event, or sometimes written as the 774/775 CE event, was not a Carrington event. It was something else entirely, something bigger by a factor that stretches the imagination. Initial analyses considered multiple possible explanations: a nearby gamma ray burst, a supernova, a comet impact. One by one, these alternatives were largely ruled out or found to be insufficient explanations. The current scientific consensus, though not unanimous, is that the 774/775 CE event was caused by an extreme solar proton event, an eruption from the sun of protons with such high energy and such enormous fluence that they bombarded Earth's atmosphere at a rate 20 times higher than anything in the modern record. A second event of similar character was identified in tree ring data from approximately 993 CE, roughly half the magnitude of the 774/775 event, but still far outside the range of anything recorded in the modern instrumental era. And in 2023, a third event was identified in data from approximately 660 BCE, comparable in magnitude to the 774/775 event. Let that sink in. In the 10,000-year record of cosmogenic isotopes, the deepest proxy record we have for extreme solar events, there are at least 3 events of this class. 2 of them are comparable to or larger than anything we had previously thought the Sun could produce. Their recurrence interval based on 3 data points is very roughly 1 every 2 to 3,000 years, though with enormous uncertainty given the small sample size. The 774/775 CE event has been studied intensively since its discovery. Researchers have tried to calculate what a comparable event would mean for Earth today. The conclusions are genuinely alarming. An event of this magnitude would not just affect the power grid and satellites. The high-energy proton flux would significantly deplete the ozone layer. Globally, not just at high latitudes. Models suggest ozone depletion of 10 to 40% globally for 1 to 2 years following such an event, with the recovery timescales of a decade or more depending on assumptions about the event's proton spectrum and atmospheric chemistry. 10 to 40% ozone depletion. For perspective, the Antarctic ozone hole at its worst represented ozone depletion of roughly 60% over Antarctica, a regional and seasonal phenomenon that produced measurable increases in UVB radiation reaching the surface, measurable increases in skin cancer rates in affected populations, and documented effects on marine phytoplankton and amphibian populations. A global, sustained ozone depletion of 10 to 40% following an extreme solar proton event would be in a different category entirely. The increased UVB flux reaching the surface would stress or kill photosynthetic organisms, phytoplankton in the upper ocean, crops in unshielded agricultural settings. The effects on unprotected animals, including humans, would range from severe sunburn to dramatically elevated cancer rates. The agricultural and ecological consequences would be profound. This is the upper range of what the sun is physically capable of, not what it does routinely, not what it does every century, what it has demonstrably done at least twice in the past 1,500 years, and what it is physically capable of producing at the extreme end of its event distribution. And now we come to the specific nature of what is being hidden, because this is where the story gets genuinely strange. The 774/775 CE event occurred. People were alive in 774 CE. The Carolingian Empire was consolidating power in Western Europe. The Tang dynasty was in its final century in China. There were astronomers in Baghdad, scholars in Constantinople, monks copying manuscripts in Ireland. None of them recorded anything remarkable happening in the sky that year. There are no contemporary accounts of extraordinary aurora, no descriptions of unusual atmospheric phenomena, no records of electromagnetic disturbances, because there was no electromagnetic infrastructure to disturb. The trees recorded what the humans missed. The event was happening. The sun did it. The atmosphere absorbed an unprecedented proton bombardment. The cosmogenic isotope spike is permanent, preserved in wood and ice across the entire planet. And the people of 774 CE went about their lives, largely unaware that something extraordinary was occurring above them. The sun's capacity for extreme behavior is not a modern discovery. It is a permanent feature of its physics. We are the first civilization complex enough to be seriously vulnerable to it, and we are in the process of becoming the first civilization with instruments sensitive enough to detect its precursors and understand its mechanism. That is the race. Not between us and the sun exactly, between our understanding and our vulnerability. Our vulnerability has been growing for 2 centuries, accelerating in the past 50 years, and is accelerating faster now as every aspect of modern infrastructure becomes more dependent on electromagnetic systems, satellite communications, and grid-based power. Our understanding is also growing, but not as fast, and not without the gaps we have been discussing throughout this journey. Here is what we know about predicting extreme events specifically. The most energetic solar proton events require a specific combination of factors: a large, active region with complex magnetic topology, a flare that accelerates particles effectively. Not all flares do this equally, and the relationship between flare size and particle acceleration efficiency is not fully understood. A coronal mass ejection that propagates in exactly the right direction and at the right speed to drive a sustained shock that continues accelerating particles over a period of hours. A geomagnetic field configuration at Earth that allows those particles to access the atmosphere at low latitudes rather than being deflected toward the poles. Each of these factors involves physics we understand partially but not completely. The magnetic topology of active regions can be assessed from surface magnetograms, measurements of the magnetic field direction and strength across the solar surface, but the three-dimensional structure of the field above the surface, in the corona where eruptions originate, cannot be directly measured. It must be inferred from models, and those models are known to have significant errors in complex topological configurations. The particle acceleration efficiency of flares depends on details of the magnetic reconnection process, the rapid reconfiguration of magnetic field lines that releases stored energy that occur at spatial scales too small for current instruments to resolve directly. The physics of reconnection in the solar corona is an active research frontier. We know it happens. We have detailed theoretical frameworks for how it works. We cannot yet predict which specific events will produce high-energy particle acceleration and which will not. The direction and speed of a coronal mass ejection can be estimated from coronagraph observations, spacecraft that block the bright solar disk to image the fainter corona. But the precision of these estimates is limited, and the evolution of a CME as it propagates through the solar wind involves interactions with preceding structures that are difficult to predict in detail. All of these limitations mean that the warning time for an extreme solar proton event is currently measured in hours at best, and that distinguishing in advance a flare that will produce a dangerous particle event from one that will not remains beyond our reliable predictive capability. There is active work on every one of these fronts. Machine learning approaches applied to solar magnetogram data have shown promise in identifying active region configurations at high risk of producing major flares. Pattern recognition across thousands of historical events, identifying the magnetic configurations that preceded large flares in the observational record. These approaches are producing genuine improvements in flare probability forecasts, though they remain probabilistic rather than deterministic, and struggle with rare extreme events precisely because the training data set for rare extreme events is small. There is also work being done at a more fundamental level, using the new interior flow data from helioseismology and the coronal magnetic field, models being developed with solar orbiter data to build what researchers call whole sun models, end-to-end simulations of the solar magnetic system, from the dynamo deep in the interior to the coronal structures where eruptions occur. These models do not yet run in real time and are not yet accurate enough to be operationally useful for space weather forecasting. But they represent the direction the field is moving, and the trajectory of improvement over the past decade has been substantial. There is a parallel effort focused not on prediction, but on detection, building a more comprehensive network of space weather monitoring assets that can provide earlier and more detailed warning of approaching solar events. The current monitoring infrastructure centered on DSCOVR at the L1 point gives us a real-time measurement of the solar wind conditions arriving at Earth's magnetosphere, but the L1 point is only about 1.5 million kilometers from Earth, approximately 1% of the Earth-Sun distance. A coronal mass ejection traveling at typical speeds of 500 to 800 kilometers per second arrives at L1 roughly 30 to 60 minutes after it passes that point. Alternative monitoring positions have been proposed and studied: a spacecraft in a heliocentric orbit trailing Earth by 60 degrees at the L4 or L5 Lagrange points would provide views of solar active regions as they rotate toward Earth several days before they are directly facing us, potentially extending warning times to days rather than hours. The European Space Agency has proposed the Lagrange mission to place a spacecraft at the L5 point, specifically for space weather monitoring. It has not yet been funded for full development. The gap between what we know we should build and what we have actually built is a persistent feature of space weather preparedness. The scientific case for improved monitoring is unambiguous. The economic case, weighing the cost of monitoring infrastructure against the probabilistic cost of extreme events, is also clear, given the damage estimates for a major event. But translating clear scientific and economic cases into funded missions requires political will and budget prioritization that has historically been difficult to sustain for a threat that is probabilistic rather than certain, and that has not produced a major catastrophic event within living memory. The absence of a recent catastrophe is the preparedness problem. The Carrington event is 166 years ago. Nobody alive experienced it. The 2012 near miss was not a hit. It passed behind Earth, caused no damage, and received 2 days of news coverage before disappearing from public consciousness. The preparedness funding cycle runs on incident response timescales, not on risk management timescales. We fund the prevention of things that recently happened, not the prevention of things that are statistically inevitable but temporally unpredictable. This is a known failure mode in risk management. It has a name, the availability heuristic, and it governs not just public behavior but institutional behavior and policy behavior. The infrastructure most vulnerable to extreme space weather is mostly owned by private entities, utilities, satellite operators, pipeline companies, for whom the calculus of hardening investment is constrained by quarterly earnings cycles and regulatory frameworks that do not currently mandate space weather resilience at the level the risk profile would justify. There are exceptions. Some utility operators in high-latitude countries, Scandinavia, Canada, have invested meaningfully in grid hardening against geomagnetic disturbances, partly because they have experienced significant disruptions from moderate events and have operational experience of the vulnerability. The 1989 geomagnetic storm that knocked out the Hydro-Quebec power grid, leaving 6 million people without power for 9 hours and causing hundreds of millions of dollars in damage, was not a Carrington-scale event. It was a large but not extreme event. It was enough to motivate serious hardening investment in the Canadian grid. Most of the world has not had that experience. Most of the world's grid operators have not experienced a geomagnetic storm large enough to cause visible damage. And so the investment case, pay now to harden against an event that has not happened and whose timing cannot be predicted, runs into the same psychological and institutional barriers that all low-probability, high-consequence risk management runs into. The Sun does not operate on human institutional timescales. It does not wait for funding cycles or policy reviews. It has been running its magnetic dynamo continuously for 4.6 billion years, cycling through quiet and active phases, building and releasing enormous magnetic energy structures, occasionally producing events of extraordinary violence. The 774/775 CE event did not pause while civilization prepared for it. It happened. The trees recorded it. Nobody was watching, and nobody needed to be, because nobody had anything to lose. We have things to lose now. Enormous things. The entire scaffolding of modern civilization is electromagnetic in its foundation. Power, communications, navigation, finance, logistics. Every one of these systems operates through or depends on technology that is vulnerable to the sun's most extreme behavior. And we are in a period where the sun, having just come through a modern grand maximum, is entering a phase of transition whose character we cannot fully predict, where the models disagree about whether the coming decades will bring reduced activity or continued moderate activity, where the new data from Parker and Solar Orbiter is already overturning assumptions, and where the physical upper limit of what the sun can produce is higher than almost anyone outside the specialized research community knows. There is one more hidden thing, the deepest one, and it requires us to step back from the immediate concerns of space weather and infrastructure and look at the sun in its largest context, not as a threat to manage, but as a system to understand. Because the deepest thing the sun is hiding is not a danger, it is a revelation. And it concerns not what the sun will do to us, but what the sun tells us about where we are, when we are, and what comes next for everything. The sun is middle-aged. It has been burning hydrogen for 4.6 billion years, and it has roughly 5 billion years of main sequence life remaining. In cosmic terms, it has reached half-time. But that description, while accurate, conceals something important about the specific moment in the sun's life that we are living through, something that researchers studying stellar evolution and the long-term fate of the solar system have come to recognize as a significant peculiarity. We are living through an interval that is, in multiple independent senses, a window. A period of time that is bounded on both ends by conditions substantially less favorable for complex life than the conditions we currently enjoy. Understanding what that window looks like from the outside and understanding its width, its stability, and what closes it is the work that connects every other topic we have covered into a single, coherent picture. And that picture has a shape that nobody expected when researchers began assembling the pieces. The concept of a habitable zone is familiar to most people who follow space science. It is the region around a star where conditions are right for liquid water on a planetary surface, not too hot, not too cold. The Goldilocks zone. Earth sits comfortably within it. Mars is near the outer edge. Venus is inside the inner edge, baked by a runaway greenhouse effect that turned it into a world of sulfuric acid clouds and 465-degree surface temperatures. But the habitable zone is not static. It moves. And it is not the only constraint on habitability. There is a second concept, less widely known, that operates on a different axis. Not distance from the star, but time. It is called the galactic habitable zone, and when you combine it with the stellar habitable zone and add the temporal dimension, something remarkable emerges about the specific moment in cosmic history that we occupy. The galactic habitable zone is the region within the Milky Way where conditions are favorable for complex life, far enough from the dangerous radiation environment near the galactic center, close enough to the galactic disk to have access to the heavy elements produced by previous generations of stars, in a region with relatively low density of neighbouring stars to minimize the frequency of gravitational disruptions and nearby supernova events. Earth sits within the galactic habitable zone. This is not a coincidence. It is part of the explanation for why we exist here rather than elsewhere. Now add time. The galactic habitable zone was not always habitable. In the early universe, the heavy elements necessary for rocky planets and biological chemistry, carbon, oxygen, nitrogen, phosphorus, iron, were not yet abundant. Stars had to live and die through multiple generations to build up the metallicity of the interstellar medium to levels that allow Earth-like planet formation. This process took several billion years. The galactic habitable zone in the temporal sense opened gradually over the first several billion years of the universe's history. The universe is approximately 13.8 billion years old. The Sun formed 4.6 billion years ago. Earth's complex biosphere has been developing for roughly 600 million years, counting from the Cambrian explosion. We are here, now, asking these questions at a specific point in the history of a specific galaxy in a specific cosmic epoch, and that specific point is unusual in a way that has a name. It is sometimes called the Age of Stars. We are living in the period when the universe is old enough to have produced multiple generations of stars, enriching the interstellar medium with heavy elements sufficient for rocky planet formation and complex chemistry, but young enough that Sun-like stars, G-type main sequence stars burning hydrogen stably for billions of years, are still abundant and in their prime. In the far future, star formation will decline. The interstellar gas that feeds new star birth is being consumed faster than it is replenished. The rate of new star formation in the Milky Way is already substantially lower than it was several billion years ago. Over the next several tens of billions of years, fewer and fewer new stars will be born. The existing stars will age and die. The stellar population will shift toward longer-lived, but dimmer and less energetic red dwarf stars, which dominate by number already, but are not the same kind of environment as a Sun-like star. Whether red dwarf systems can support complex life is a genuine scientific question with no resolved answer. Red dwarfs are more magnetically active relative to their luminosity, produce more frequent flares in proportion to the energy they deliver to the habitable zone, and tidally lock their planets into synchronous rotation at habitable zone distances, one side permanently facing the star, the other permanently facing away. The atmospheric dynamics, the water distribution, the magnetic field environment of a tidally locked planet around a flare-active red dwarf are very different from Earth around the Sun. They are not obviously impossible for life, but they are not the environment we are in. The environment we are in, a moderate G-type star in middle age, in a quiet phase of the galactic habitable zone, at a moment when the universe has just enough heavy element enrichment for complex biochemistry, is the environment that produced us. And it is an environment that is time-limited in ways we have been exploring throughout this discussion. The Sun will leave the main sequence in approximately 5 billion years. Before that, somewhere between 500 million and a billion years from now, Earth's surface habitability for complex life ends due to the brightening Sun and the CO2 drawdown we described earlier. The galactic habitable zone in the temporal sense will persist for billions of years, but the specific conditions that produced us, this star, this planet, this moment, are not permanent fixtures of the universe. They are a window that opened, that we are inside, and that will close. Understanding the width of that window, and specifically understanding what the sun is doing and going to do within it, is not just a scientific project. It is the project of any civilization that takes its own long-term future seriously. Not because the closing of the window is imminent by human standards. 500 million years is an almost incomprehensible span of time. But because the smaller windows within the larger window, the space weather windows, the solar cycle windows, the infrastructure vulnerability windows are not 500 million years away. They are here, they are active, and they are connected to the deeper physics of the same system. Now, let us bring all of these threads together and talk about what the next several decades actually look like from the perspective of everything we have discussed. Because the conversation about the sun's hidden nature is not purely retrospective or abstractly future-facing. There is a specific observational and scientific program underway right now, in real time, that represents humanity's most serious attempt to close the gaps in our understanding. And it is producing results faster than many researchers expected. Parker Solar Probe has now completed multiple close perihelion passes, approaches to within a few million kilometers of the solar surface, inside the orbit of Mercury, inside the outer corona itself. No spacecraft had ever flown through the solar corona before Parker. The mission was designed to answer specific questions about the acceleration of the solar wind and the heating of the corona, the two problems we discussed at the beginning of this journey. It has answered some of those questions partially and raised new ones. The switchbacks we mentioned, those sudden reversals in the solar magnetic field direction detected in the solar wind close to the sun, turned out to be far more common and more structured than anyone anticipated. They appear to be related to the release of energy from the solar surface through a process involving the interaction between the convective motions of the solar plasma and the coronal magnetic field. They may be one component of the coronal heating mechanism. The data is still being analyzed. Papers are being published at a rate that reflects how much new territory Parker has opened. One finding from Parker that has received particular attention involves the identification of structures called jets and spicules at the solar surface, small-scale eruptions that happen continuously across the solar surface, each one individually tiny by solar standards, collectively representing an enormous amount of energy transport. The idea that coronal heating might be distributed across millions of small events rather than concentrated in large ones, the nanoflare hypothesis proposed by Eugene Parker himself, the scientist after whom the probe was named, has received significant support from these observations. The corona appears to be heated, at least in part, by a continuous drizzle of small energy releases rather than by occasional large events. This changes the way we think about coronal dynamics and potentially about flare and CME prediction. If the corona is maintained by a continuous background of small events, then the build-up to a large event, the accumulation of magnetic energy in an active region that eventually releases catastrophically, happens against a background of constant small releases. Understanding how the small releases relate to the large ones, whether the small events drain energy that might otherwise feed a large flare, or whether they are dynamically unrelated, is a question with direct implications for space weather forecasting. Solar Orbiter, meanwhile, has been making its way outward from the ecliptic plane with each Venus gravity assist. Its imaging of the solar surface has already revealed structures at mid-latitudes that the models did not predict, including what appear to be large-scale organized flows that don't match the expected convective pattern. The polar region imaging, when it reaches sufficient inclination in the late 2020s, is anticipated with the kind of scientific excitement that comes when everyone in a field knows that the answer to a long-standing question is about to arrive, and nobody is quite sure whether the answer will be satisfying or destabilizing. There is a third mission that deserves attention in this context. The Chinese National Space Administration's ASO-S mission, launched in 2022 and formerly known as Quafu-1, is conducting simultaneous observations of the Sun's magnetic field, solar flares, and coronal mass ejections from a Sun-synchronous orbit that allows continuous monitoring. This is significant, not just for the science it produces, but for what it represents: the entry of a third major space agency into the front ranks of solar observational capability. The solar science community is genuinely international in a way that reflects the universality of the threat the Sun poses, and increasing the number of independent observational platforms improves the coverage, redundancy, and cross-validation of solar monitoring. There are proposals on the table for the next generation of solar observatories that would extend the monitoring network in ways that fundamentally change the warning time problem. A mission to the L5. Lagrange point, as mentioned, would give us a 60-degree side view of the Sun, allowing active regions to be tracked for days before they rotate into Earth-facing position. A mission to solar polar orbit. Not just an inclined orbit like Solar Orbiter, but a true polar orbit would allow continuous monitoring of both poles, watching the seed field for each cycle develop in real time. A mission carrying a next-generation coronagraph capable of imaging coronal magnetic fields directly, not inferring them from surface magnetograms, would eliminate one of the most significant gaps in CME and flare prediction. All of these missions are scientifically justified. All of them have been studied in detail. None of them are currently funded for flight. The funding landscape for space weather research sits in an uncomfortable middle ground. Too applied to attract the largest science funding allocations, too scientific and long-term to attract infrastructure funding, too diffuse in its risk profile to attract the focused emergency response funding that a specific disaster would generate. This is where the story of what the Sun is hiding connects most directly to a human choice. Because the Sun is not hiding these things maliciously. It is not concealing its secrets. The secrets are there in the data, waiting for the instruments and the mathematical frameworks and the computational power to read them. We are the ones who have chosen, collectively and repeatedly, to not quite fully fund the reading. Not entirely. The progress has been real. Parker and Solar Orbiter represent serious commitments of scientific resources. The Inouye telescope is producing images that are changing the field. The machine learning approaches to flare prediction are improving measurably with each cycle of training data. The helioseismology community is extracting interior information from the Sun's surface oscillations at steadily improving resolution. The cosmogenic isotope researchers are extending the deep proxy record and finding new, extreme events that inform the statistical picture of recurrence. But the pace of understanding relative to the pace of vulnerability growth is the number that matters. Every year, more satellites are deployed. Every year, more of the global economy runs through grid-dependent digital systems. Every year, the integration of GPS timing into financial clearing, logistics, and communications deepens. Every year, the common mode vulnerability of the electromagnetic civilization grows. And every year, The sun continues to do what it has always done, cycle through its magnetic rhythms, build and release energy in its corona, produce the spectrum of events from the routine to the extraordinary, occasionally reaching toward the upper limits of what its physics permits, indifferent to the civilization that has grown up in its light, and that now depends on conditions that the sun has no particular reason to maintain. There is something profound in this asymmetry. We have built a civilization predicated on electromagnetic stability. The entire modern world, every device you own, every transaction you make, every conversation you have through any network, depends on conditions that are ultimately subject to the behavior of a star we do not yet fully understand, whose most extreme behaviors we cannot reliably predict, and against whose worst-case events we are not adequately protected. This is not a counsel of fear. It is a description of where we are and an argument for where we need to go. The solar physics community knows what needs to be known. The engineering community knows what needs to be built. The policy community has been given the assessments. What remains is the translation of knowledge into action at the scale the risk profile requires. The sun gives us gifts that are easy to enumerate: light, warmth, the energy that drives the water cycle and the wind, and, through photosynthesis, almost all biological productivity on the planet, the magnetic field that sweeps the solar system and protects us from the worst of the galactic environment. These gifts are so foundational to our existence that we rarely think about them as gifts. They are simply the conditions in which we live. The sun also withholds things, not deliberately, not through any intent, simply through complexity, through the fact that it is a physical system of staggering depth and intricacy operating on scales of space and time that dwarf human experience, governed by physics that we have been unraveling for centuries and that continues to surprise us every time we look more carefully. What it is withholding, specifically, is the timing. We know the catalogue of what it can do. We know the energy scales. We know the mechanisms partially. We know the recurrent statistics roughly. What the sun will not give us, what the gaps in our models and monitoring prevent us from having, is the specific date, the specific storm, the specific moment when the quiet middle-aged G-dwarf at the center of our solar system decides, through the blind operation of physics, to release a fraction of its stored magnetic energy in a direction that matters to us. The 774/775 CE event happened on a specific day. Nobody alive then knew it was coming. Nobody alive then would have been harmed by it. Nobody alive today was there to record the warning. The trees remember. The ice remembers. The isotope ratios preserved in wood and frozen water across the entire planet remember. The question is whether we will be the first civilization to remember in advance. The first civilization to look at what the trees and the ice have recorded, at what the new instruments are revealing, at what the models are beginning to show us about the nested rhythms of the solar dynamo, and to act on that knowledge before the event rather than after it. The answer to that question is not written anywhere in the solar data. It is a human question. It depends on whether the understanding we are building through Parker and Solar Orbiter and Inouye and ASO-S, and the next generation of instruments that need funding, and the mathematical frameworks that need development, and the operational systems that need engineering, accumulates fast enough, and is taken seriously enough, and is translated into physical resilience robustly enough before the statistical window closes. Because the statistical window will close, not in a metaphorical sense, in a literal, probabilistic sense. The events are real. They have happened. The recurrence intervals are finite. 12% per decade for a Carrington scale event means that over a 50-year period, one human generation. The design lifetime of major infrastructure. The cumulative probability of a direct hit approaches 50%. Add the possibility of an event exceeding Carrington by a factor of 10, with a recurrence interval measured in centuries to millennia, and the probability distribution has a tail that is not negligible on civilization-relevant timescales. We are inside that tail right now. We have been inside it for as long as we have had electromagnetic civilization. We will remain inside it for as long as the sun continues to produce the magnetic activity that drives its cycle, which is to say, for the remaining 5 billion years of its main sequence life, minus the roughly 500 million years before Earth's complex biosphere ends, minus the window of time before some other civilization-ending or civilization-transforming event intervenes. 500 million years is a long time to be inside a probability distribution. The question is not whether an extreme event will occur. The question is whether it will occur before or after we have adequately protected ourselves against it. The sun does not know we are here. It has no awareness of the civilization that has grown up in its light, that has studied it intensely for decades, that has sent probes flying through its outer atmosphere, that has built instruments of extraordinary sensitivity to watch its surface and sound its interior and measure the particles streaming out through its corona. It is a physical system. It follows physics. But we know it is there. We know what it has done. We know what it can do. And we now know, in a way that was not possible a generation ago, that the things it has been hiding from us are not permanently hidden. They are within reach of our instruments, our mathematics, and our understanding. Every close pass of Parker Solar Probe, every high-latitude image from Solar Orbiter, every vibration of the solar surface read by helioseismology, every ring of ancient wood storing the memory of a storm that nobody saw. These are pieces of a picture that is assembling itself, slowly, in the datasets of thousands of researchers working across dozens of countries and institutions, building toward the moment when the sun's deepest hidden rhythms are finally legible. When the prediction problem yields, not completely, not with absolute precision, but enough to give us warning, enough to give us time, enough to close the gap between what the sun is capable of and what we are capable of surviving. That moment is not here yet. The picture is not complete. The sun is still hiding things. But the hiding is not permanent, and we are closer to the reading of it than we have ever been. The light takes 8 minutes to reach us from a star we do not fully understand. The neutrinos arrive in the same 8 minutes, carrying messages from the core that we have only recently learned to decode. The particles from an extreme event travel faster through space than the storms they presage, arriving at our instruments before the worst of the effects if we have instruments positioned to catch them and systems fast enough to respond. 8 minutes, 150 million kilometers. Between a star burning 4 million tons of mass into energy every second and a civilization that has built its entire existence around the assumption that the light and warmth and electromagnetic quiet will continue. The assumption is mostly justified. The sun is a stable, reliable, middle-aged star. The probability of catastrophe on any given day is low. The probability over a civilization's lifetime is not. We know this now. We know it because the trees remembered, and the ice remembered, and the instruments we sent into the sun's own atmosphere came back with data we did not expect. We know it because the neutrino detectors confirmed what the models predicted, and then required us to revise the models of the particles themselves. We know it because the coronal heating problem and the interior convection problem and the grand minimum hypothesis and the Miyake events and the 2012 near-miss all point at the same underlying truth. The sun is not hiding these things to protect us from knowing them. Physics does not work that way. It is hiding them because they are deep. And because looking deep requires effort and time and instruments and mathematics and funding and the slow accumulation of understanding that science always requires. The sun is bigger than we thought, not in size. Well, we knew the size. Bigger in complexity, bigger in the range of its behavior, bigger in what its history encodes about the past and what its physics promises about the future, bigger in what understanding it means for the civilization living in its light. The countdown that matters most is not the one to Earth's eventual uninhabitability, 500 million years away. It is not the countdown to the sun's red giant phase 5 billion years away. It is not even the countdown to the next Carrington scale event, uncertain in timing but certain in eventual occurrence. The countdown that matters most is the one we are running against ourselves. The race between the growth of our understanding and the growth of our vulnerability, between what we are learning about the star at the center of our solar system and what we are building that depends on that star continuing to behave within the range we have planned for. That race has no finish line. It is ongoing. It was ongoing in 774 CE when the trees recorded what the people missed. It is ongoing now as Parker makes its closest approach and solar orbiter tilts toward the poles and the Inouye telescope resolves convective cells 30 kilometers across on a star 150 million kilometers away. We are the first civilization to know what we know, to have seen the Miyake events in the data, to have watched the 2012 near-miss pass behind us, to have built instruments that fly through the sun's own atmosphere and return data about a place no probe had ever been, to have solved the solar neutrino problem and discovered in solving it a crack in the most successful theory in physics, to have looked at the coronal heating problem and known with precision exactly what we do not understand. This is an extraordinary position to be in. Not comfortable, but extraordinary. The sun has been burning for 4.6 billion years. It has another 5 billion years to go. In that vast span of time, we occupy an almost imperceptibly small slice. A few centuries of technological civilization, a few decades of serious solar science, a few years of unprecedented close observation. In that slice we have learned more about the sun than in all of previous human history combined, and in learning it we have discovered that what was hidden is larger, stranger, more consequential, and more within reach than we imagined when we started looking. The sun is hiding something for a reason. The reason is that everything deep is hidden until you look hard enough, long enough, with instruments precise enough, and minds open enough to receive what the universe is actually showing you rather than what you expected to find. We are looking. We are learning to look better. The picture is assembling. What it shows us when it is finally complete will be the most important thing any civilization has ever understood about the star it lives beside. We are not there yet, but we are closer than we have ever been. And the sun, for all it conceals, has already shown us enough to know that the looking is worth it, that the understanding is achievable, that the gap between what we know and what we need to know is real and finite and closable. That is not a small thing to know. In the darkness between stars, in the silence of a universe that offers no guarantees and follows no agenda, it is perhaps the most important thing we know. The clock is running, the star is burning. The data is coming in. We are paying attention.